Hello and welcome to this video on this asynchronous day. Hope you're having a good day. It's always a good day to learn some physics. And today we're going to talk about these things, Atwood machines. Why are they called Atwood machines? I don't know, right? But if you're really curious, you can Google it. But the idea is an Atwood machine is when you have two masses connected by a rope, and I should probably also say in tension. So this is a rope that's completely taut. And we have a pulley, and very importantly, this pulley has no mass. If the pulley had mass, that would cause a lot of other complications in our application of the second law, right? And we'll eventually get to that scenario later. But as of now, we're just going to say the pulley has mass. So I know you guys have been trying to understand torque for the past few days, but let's take a detour and talk about these things because it really doesn't take that long to understand them, and there's not really a good place to fit them in so far. So I'm just going to do it on this asynchronous day. I would take notes, write down these examples, and just know you'll see these sort of going forward. Probably not on the most the closest quiz in our near future, but maybe later on. So anyway, we have a massless pulley. Let's just suppose there's like an axle bolting it to the wall, so it's going to stay in place. And we are currently holding this this mass in place. It's a really big arm, but the idea is you let it go, and you try to see, okay, how is this system going to move, right? Is this mass going to go down? This mass go up? Is it going to be the opposite, right? I think a lot of you guys, if you have a good head on your shoulders, you'll realize that this should be kind of the correct intuitive way the system will move. You know, the 3 kilogram mass is heavier, and so it's going to be pulling a lot harder due to gravity than the gravity acting on the 2 kilogram, right? So the system is going to experience a greater force from the 3 kilogram block. All right, so how do we actually approach this and maybe get some solid calculations here, right? So the point is, if I am going to start to move down the 3 kilogram mass and the 2 kilogram moves up, because they're attached to the same rope, if the 3 kilogram mass moves down 2 meters, then the 2 kilogram mass will also move up 2 meters, right? They should correspond to each other. But also we can ask a more interesting question, which is, okay, what is the acceleration of block 1? What is the acceleration of block 2, right? This being block 2, this being block 1. And I should actually move this here. Oh, nope, they didn't like that. Yeah, I'll just leave it, right? So one thing we might want to point out that maybe some of you guys don't see as obvious, but notice how the blocks are always moving in different directions, and therefore their accelerations are going to be different. So like if I know that the acceleration of block 1 is 3 meters per second squared, that automatically guarantees that the acceleration of block 2 is going to be negative 3 meters per second squared. That's going to be a really important fact, right? This is kind of an if and only if sort of statement, right? They're going to always do opposites of each other. So where should we begin? Let's begin with some free body diagrams. So I'm going to do the free body diagram for block 1 first. So I have a dot. This is the 2 kilogram mass, right? And it's going to pull down. The force of gravity, is pulling down on it with 20 newtons. And we don't know what the tension force is, but our intuition told us it should be accelerating upward. So if it has a net acceleration upward, the net force needs to be upward. right? The only way that's true is if the force of tension from the rope is bigger than the force of gravity. In fact, I did a big no-no. I need to actually label these with the proper names. Right, so in this case, the force of tension is bigger than the force of gravity. Right, we can conclude this because we know which direction it's going to accelerate in. If I do the free body diagram for block 2, this is the 3 kilogram block. Draw a dot. We have a much greater force of gravity. So something like this. And, in fact, we know how big, right? This one was 20 newtons. This one is going to be 30 newtons, right? So it should be bigger. What is important to point out, though, is that the tension, because this is the same rope, is going to be the same, pulling up. But notice, in this case, the tension force is smaller than the force of gravity. Very important. Okay, so now that we have some diagrams, let's go ahead and set up Newton's second law. Just like always, just like good old times. Okay, so sum of the forces equals the mass times the acceleration. Now when I apply this to block 1, right, the forces I get are the tension, pulling up, and then I have minus 20. Those are the 20 is the force of gravity of this 2 kilogram block, right? 2 times 10. We don't know what the tension is. We don't know how big it is. And then the mass is going to be 2 times the acceleration of block 1. So I'm going to call that A1, acceleration of block 1. If I apply Newton's second law to the second block, I get the tension pulling up, again, just like the other block, then minus 30. And this equals 3 times 8. All right? In fact, this is A2, right? This is the acceleration of block 2. So, where do I go from here? Well, what I do is I use this fact, right? The fact that the accelerations are going to have the same magnitudes but opposite directions. So what I can do is I can make a little substitution. So instead of A2 should be the same as negative A1, right? It is the same acceleration as A1 but the opposite direction. So I'm making it negative. Again, it's just coming from this fact, right? And once I do that substitution, I now have a system of equations. I have this equation and this equation. There's 2 unknown variables and there's 2 equations. That's something that's solvable, right? So there's a lot of ways you can do this. Here's maybe what I would do. Let's just go ahead and solve for T. Solve for the tension force. So tension equals 2A1 plus 20. This equation tells us that the tension force equals 30 minus 3A1. And what do you know? I can just set them equal to each other. So I get 2A1 plus 20 equals 30 minus 3A1. Do some algebra. I don't want to spend too much time on algebra here, but I'm just going to go for it. Subtract the 20, add the 3A1 over, divide by 5, and you get that A1 equals 2 meters per second squared. Does that make sense? So it's positive, right? So that's telling me the 2 kilogram block is going to accelerate upward at 2 meters per second squared. That actually matches our intuition. We just didn't know what the number was. But we did know it was going to accelerate upward. And likewise, this automatically implies that A2 is going to be negative 2 meters per second squared. Again, this should make sense, right? The 3 kilogram block we expect to accelerate downward, but the same magnitude, but opposite direction as before. So now, here's one thing that you can do if I've been very careful with my subscripts here, right? Like differentiating A1 and A2. If you're not the most detail-oriented guy out there, let me show you a little trick that you can do. So take this scenario, but imagine making it flat. So flattening out everything. So instead of even having a pulley, it's going to look a little weird, but imagine putting these blocks side by side, connected to a rope, and imagine, right, the forces acting on these two blocks also turning as you straighten out the rope side by side. So the way this is going to look, if you're going to do it this way, and for some people this is easier, right, is that the force of gravity acting on this block pulls to the left. The force of gravity acting on this block pulls to the right. And then you have tension and tension here. So the tension forces are equal. These are actually different forces. So I'll call this FG1, FG2, right? They're different sizes. The idea is if you treat this as a system, so imagine the rope and the two blocks are just one thing, and you do Newton's second law, you get a very simple calculation, right? So you have FG2 pulling to the right minus FG1. And now the total mass of the system is 5. And it just accelerates either left or right. So we can just say it has an acceleration, right? There's not, since we're treating it as a system, it's just one object with one acceleration. And FG2 would correspond to the 30 newtons. FG1 would correspond to the 20 newtons. And of course we have 5A. Notice how we get the exact same calculation. We just arrived at it in a very different way, right? So we kind of broke gravity here because we're making it work sideways, right? These sideways forces. That's not how gravity works, but this is a good mental trick you can do if you don't, this was a lot of work over here. Now this is the proper way to do it. This is the more valid way to do it that you would actually get full credit for. But this would help you get the exact same answer, right? So this is saying it's accelerating to the right. Even though we know that's not going to happen, right? We can kind of tell if you put the system back to the way it used to look, this would correspond to the 3 kilogram mass moving down and the 2 kilogram mass moving up, right, with this acceleration. So yeah, notice how we get the same answer, two very different approaches. One is a system-based approach. This one is more like individual blocks, right? I think this is the best way. This is what the AP graders are looking more for. This is more organized, more clear. This is more of like a little quick trick, right? If you're just trying to solve a problem really quickly. Notice how we didn't have to worry about the tension forces because they were internal. So we do not put them in our sum of the forces. So anyway, this is like the starter Atwood that everybody starts with every single year. This is kind of my main go-to. And then we move on to some other kinds. So this is another kind that's out there. So you have a block on a frictionless surface. Now you could add in friction, but we're not going to because this is our first day on Atwoods. And so let's just think about this. So what do we expect to happen, right? So Gravity is going to pull down on this 2 kilogram block, and we're going to have a tension force pulling up. Do we know how big that tension force is? Maybe. Over here, right, we're going to have gravity pulling down on this. We're going to have the normal force, and then we're going to have a tension force pulling to the right. So this would be Fn, Ft. Oh, I'll just use T. I like using T. This is Fg1. Let's just call this Fg2. And this would also be T. Now, if you just think of the fact that there is no friction, right? Look at this block over here. We expect this block to move to the right by virtue of the fact that this is an unbalanced diagram, right? The net force in this case is not zero, clearly, especially horizontally speaking, right? There's only a force pulling to the right. There should be an acceleration to the right. What that means is we should expect this block to move down, right? So it's going to have an acceleration this way, whereas this block is going to accelerate to the right, right? And that's what we should expect when we release the blocks. So I'm going to do this kind of my way first. I like this way. And you could also probably use this approach. We'll do it in a second here. So FBD1. This is for the 3 kilogram block. All right, so now in this case, we know that the gravity force and the normal force are going to cancel. Well, no, I should still put the forces on the diagram. You have to. Yeah, let's just put them there. All right, so this is force of gravity 1. And this is going to be 30 newtons. So will this be, right? Otherwise, the block would somehow fly in the air or go through the floor. And then we have that tension force. FBD2. 2 kilogram block. This one is going to have the same tension force but pulling up. And then it's going to have a bigger force of gravity pulling down. And that's going to be a 20 Newton force. We don't know how big the tension is, right? All we know is that the force of gravity pulling down on block 2 is going to be bigger. How do we know this? Because we already concluded that it has a downward acceleration. If it's accelerating in that direction, the net force needs to be in that direction. Newton's second law. So now we got these diagrams. Let's move on to the second law. And let's just start off doing it just in the horizontal direction because that's the direction that the first block is going to accelerate in. So I'm specifically going to do all of the x components of everything, right? So there's only one force here, that would be tension. So the magnitude of tension should equal the 3 kilogram block times its acceleration. And that's it, right? So this is one relationship between tension and acceleration. Over here, though, notice my tension force is now vertical, and my acceleration is going to be vertical too. So for this free body, I'm probably going to use Newton's second law in the y direction. So I get the magnitude of tension minus Fg2, the magnitude of Fg2, equals 2 times the same acceleration. In fact, you know what? Let me go ahead and differentiate these accelerations. So we'll call this A1 and A2 again. Let's think about the connection between those two accelerations. So like A1 over here is going to be positive, right? Because we know it's going to be to the right for the first block. Notice how A2 is downward, if it's a vector. A2, the magnitude of this thing, or sorry, not magnitude. The direction is going to be downward, which means A2 will be a negative quantity. Right? T minus FG2 is going to be negative. Right? So when we're thinking about how A1 and A2 are related, what that means is A1 will equal negative A2. Or you could say negative A1 equals A2. The point is they have the same magnitude. Right? Same magnitude, but different directions. And so that's how we got to be careful how we substitute here. So I'm not going to recopy that equation. We're going to substitute negative A1 in here, just like we did on the last problem. All right, so T minus, we also know FG2 is 20, so I'm going to put that in there. And then A2 is equal to negative A1. So there we go. And now let's substitute in, right? So I'm going to take this, put it in. So we have 3A1 minus 20 equals negative 2A1. That's going to give us 5A1 equals 20. So A1 equals 4 meters per second squared. And that means that A2 equals negative 4 meters per second squared. Again, notice how the directions and the magnitudes match what we expect, right? The negative 4 corresponds to this downward vector. The positive 4 corresponds to this vector to the right. Okay? Again, just like we did with the other problem, we can do this one in a very similar fashion if we make everything horizontal. So if I take my two blocks, I make them horizontal. Think about where all the vectors are going to go, right? And to be honest, we can kind of get rid of these two vectors because we know they're going to cancel out anyway. So, I mean, we could put them there. I guess it doesn't hurt. All right, so Fn, Fg1. And then we have tension. And then this Fg2 vector now becomes a vector pointing to the right. Fg2. So notice how this gravity vector actually stayed pointing down because we're basically just taking this block and we're kind of pulling it out over here, whereas this block is going to stay where it is. So the idea is basically the second block is the only one that moves and the vector kind of moves with it. And if we treat this as a system again, this is my system, we can run Newton's second law on it. So sum of the forces equals mass of the system times acceleration of the system. And really, the only force that doesn't cancel out, right? Keep in mind, this vector and this vector will cancel out. These two forces are internal, and they cancel out anyway, even if you did put them in there. So really, this is the only one that's going to show up in the sum. And Fg2 has a size of 20. So that's 20 newtons. The mass of the system is 5. And we solve for the acceleration. So that's 4. And we get the same magnitude answer, right? This is 4 meters per second to the right. But if we take our block and we put it back down to where it was, that would correspond to it moving down. Right. So again, this is just a little trick here, but really, like, this is the proper way. I know you're thinking in your head, this is way easier. Why the heck are you teaching us the other way? Because this is the better way. You actually have to think clearly, organize your work, label things. This is just a little party trick. It's not the proper way. Anyway, let's move on to this last example. I know it's been a while. I want to see if we can challenge ourselves here. And let's do one that's a little bit more out of the box. So this one, solve for the acceleration. Let's say A1 in terms of M1, M2, and other physical constants. Physical constants like G, right? G is probably going to show up here. So we like numbers, right? But we know AP exam, they don't like numbers. They like throwing this stuff at you guys. So we better get used to it. Let's go ahead and just rely on the work we've already done. So we kind of already have the free body diagrams, although in this case, we don't know which vector is going to be bigger, right? We only knew that due to the fact that we had like actual numbers. And so we had an intuition of like which direction things are going to go. In this case, we don't know if M1 is bigger than M2, right? Or if it's the other way around. And you know what? It does not matter at all, right? You just got to trust Newton's second law. That's all we got to do. All right, so let's just think about the forces. Don't get hung up on which is bigger or smaller. So let's just imagine them, right? All we know is tension is going to be the same applied to both masses. And there's going to be like a force of gravity here and a force of gravity here. And they're probably going to be different. All we need to know is how to calculate them in general. All right, so let me set up Newton's second law for the first one. All right, so we have the tension. It's pointing up clearly, minus the gravity. Force of gravity here is going to be M1 times G in general. And we're doing our second law on block 1 specifically, right? Which means this becomes M1 times A1. Okay, so that is Newton's first law just applied to block 1. Now, if we do block 2, let's do block 2. Sum of the forces equals mass times acceleration. Block 2, same kind of thing. It has tension pulling up on it. It has the force of gravity, but now it's M2 times G. And it's equal to M2 times A2. Okay? So again, no numbers here. Don't worry about it. We can rely on the same facts that we learned here, that the accelerations for block 1 and block 2 are going to be opposites of each other. We can make that same substitution here. All right, so what I can do is I can say, let's replace A2 with negative A1. Same thing. Okay, here we go. This is where the algebra kicks in, guys. So just like before, I'm going to solve for tension. Seems like as far as what we can do here, this is going to be the easiest approach in my mind. I'm going to add that over, and I'm going to get M1G plus M1A1. Same thing here. Solve for tension. I get something very similar but different. So M2G, notice how I get minus M2A1. Okay, because remember we made that substitution, it threw a negative in there. So what's going to happen is I set these equal to each other. And what I get is M1 times G plus M1A1 equals M2 times G minus M2A1. Let's do some algebra magic here. I'm going to get this term to the other side. I'm going to get this term over here, right? Just doing some basic algebra. This is going to give me M1, A1 plus M2, A1, right? I added it to the other side. Over here, I'm going to get M2 times G minus M1 times G. If you're having a hard time following this, just go through it very slowly, right? I just don't want to make this video an hour long here. I'm going to factor out an A1. So I get M1 plus M2. Over here, I'm going to factor out a G. M2 minus M1. And lastly, check this out. I get an expression for A1, which is the acceleration of the first block. So check this out. This is going to be way more interesting than all the problems we've done before, in my opinion. So M2 minus M1 divided by M1 plus M2. Now what we have here is a nice little functional dependence. I love this kind of part of physics. Now we get to play around with what can happen. So imagine a few cases, right? Imagine that M2 is much heavier, or sorry, let's just say it's greater than M1, right? What does this equation tell us happens? What does this tell us about A1? Well, if M2 is much greater, we get, all we can really say is that it is positive. Does that make sense with our scenario, right? If M2 is the heavier one, then that makes sense. We expect the first block to go up and the second block to go down, right? So this would be the acceleration. This would be A1. This would be A2, right? Makes sense to me. Okay. What if M1 was bigger than M2? What does the functional dependence tell us? If M1 is bigger than M2, we end up getting a negative output for A1. Right, so if M1 is the heavier block, this one, then that means that it's going to start moving down this way, and this is going to accelerate up this way. And that makes intuitive sense to me as well, right? Last little scenario here. Imagine M1 is equal to M2. What does this predict for the acceleration? It predicts that the acceleration is equal to 0. Does that make sense? Right, if these two masses are equal, M1 equals M2, and you let it go, do you expect one of them to pull down or the other one, right? We don't expect any motion, right? If they're equal masses, it's going to be balanced. If M1 is indeed equal to M2, nothing's going to move, right? That's just our intuition here, thinking. We could also do some other things too. So, for example, imagine that M1 is approximately 0, right? So this would be like if you took this mass here and you somehow reduced it down to 0.000000001 kilogram. Right, it's just this incredibly light thing. In fact, it's basically not even there. What would we expect M2, how would its motion react in response if nothing is really on the other end of the rope? Well, think about it. Essentially, M2 is just going to be in free fall. And look at this. Look at what happens to our equation. If M1 is approximately 0, then A1 is going to be approximately G times m2 over 0 plus m2. Well, that's going to be equal to g times m2 divided by m2, and the m2's cancel, and you get g. That is free fall, my friends, right? G is the acceleration you experience if you're falling in the air, right? So if one of these masses is approximately 0, we can essentially just ignore it and expect the other mass to be falling as if it was falling in the air, in free fall. So I think this approach with no numbers at all is supremely more powerful, better than all these little number problems. I know you guys like numbers, but seriously, we discovered so much more by approaching a problem this way. This is something I wish I saw more in high school. I only started seeing it really once I got to Georgia Tech, and it blew my mind. You should embrace this as well. You really should. So anyway, I've talked for long enough. Take care. Have a good Wednesday. See you around. Bye.